Hi, everyone. I'm Robert Gregg, and I'm really excited to speak with you today about the design and control of a quasi-direct drive prosthetic leg for Agile amputee locomotion as part of the IROS workshop. So first, I want to explain how our leg is different than the other legs that you're going to hear about during the workshop. So in particular, our leg is designed to optimize back drivability. Okay, so typically you're thinking of an actuator in the sense of a motor driving a load, but with back drivability, you're also concerned about the load being able to drive the motor. And so this is important for things like gravity pulling the leg down during swing motion to allow free swinging behavior like a C leg might have, a passive prosthetic leg might have, while also being able to provide large forces to propel the gait cycle during push-off. And so that is essentially the main distinction of our design, is that it's highly back drivable and can provide high torque as well. And so we take inspiration from the field of legged robots for this design and for the control. And so in particular, the MIT Cheetah has really been pushing forward this idea of quasi-direct drives. So these are motors they are high torque motors, pancake style motors that can deliver high torque. And so then you don't have to use such a large gear ratio with them. And that is what, as we'll talk about later, gives you the back drivability. And this allows really impressive dynamic performance from the robot. And we're also going to be talking about using a phase variable for the control of our robotic leg, which is inspired by work on autonomous legged robots as well. So first I want to answer the question of why we care about quasi-direct drives. And first we need to really define it. And so it's a high torque motor with a low ratio transmission. And generally speaking, the field considers less than 24:1 to be low enough for the transmission ratio. And the reason that matters is that the biggest thing that contributes to back drive torque is the inertia of the actuator. And the reflected inertia of the motor scales with the square of the gear ratio. And so as you increase the gear ratio, you actually have a much more dramatic effect on the reflected inertia that you have to then overcome to accelerate the motor during back driving. And so if you're able to design a quasi-direct drive motor, then you have the benefit of low backdrive torques, yet you can still get high output torques by virtue of the high torque motor. And so this, the first part, the backdrivability, allows free swinging knee motion, like I talked about earlier, and then the high output torques provide powerful ankle push off, which is important for the reasons that that we mostly understand. So additionally, we have high bandwidth with negligible dynamics from the actuator. So essentially, the actuator, you don't have to worry about modeling its dynamics because they're negligible. Also, it has high bandwidth, meaning that you can servo very quickly for position control. You also have very accurate torque control and impedance control, like we'll demonstrate later. We also get compliance to impacts, which is important for having smooth touchdowns during walking, and as well as the comfort to the user. So impact forces don't transfer to the residual limb in a painful way. Additionally, through the back drivability, we have high efficiency as well, and we have the ability to do regenerative braking, which will allow us to lower the power consumption of the leg by charging the battery during negative work, as well as energy sharing between the joints when one joint does negative work at the same time as another joint doing positive work. And lastly, we also have the benefit of low acoustic noise, because when you have a low ratio transmission, that usually means that you have fewer meshing rolling parts in the transmission, and that's the source of the noise. And so we actually have very low acoustic noise compared to more traditional high ratio designs. So this is our leg design. We ended up choosing a RoboDrive frameless motor which can deliver a large amount of torque, about 8 Newton meters, I believe, and a 22-to-1 compound planetary gear set that mounts to the motor. And this allows us to have very backdrivable motion like we see in this video, where the researcher is able to push it with their finger and gravity is able to pull the leg down when it is released at an angle. And so this demonstrates backdrivability when the power is entirely off. And then if you're interested in other specifications of the motor, like in the actuator, like peak torque, which is around 180 Newton meters, and backdrive torque, which is around 3 Newton meters, as well as power consumption, et cetera, then please see our 2020 Transactions on Robotics paper. So one of the features that I mentioned earlier is its ability to do position control. And so what we've demonstrated in our paper is that we can do both walking and running trajectories with very accurate tracking. This is important for its ability to perform variable cadence walking and running. Additionally, we can do very accurate impedance control even without a torque sensor for feedback. And so in this experiment, we're showing essentially an experiment where we have essentially chosen the proportional gain as our stiffness value and the damping gain as our viscosity value for the velocity gain as our desired damping. And essentially, because the actuator has negligible dynamics of its own, essentially we can just use PD control to directly render a desired impedance. And so this experiment demonstrates how accurate the measured torque is compared to the commanded torque. All right. And so based on these features, we adopted a control method that really takes the best of both worlds. So during the stance period, we're going to be using impedance control, which will give us compliant, forceful interaction with the ground, like I mentioned earlier, for nice smooth touchdowns and very powerful push-offs. Additionally, during the swing period, we're going to switch to a phase-based position control method. And so essentially using a phase variable, as we'll define shortly, will give us an indirect sense of volitional control over the foot placement, which is really important for staying synchronized to the progression in the gait cycle, for giving the user control of where they plant their foot, important for stability and lots of other things. So during the stance phase, what we do is we actually just plug in biological joint impedances that we found in the literature. So for example, if we take a quasi-stiffness value, we will plug it in to the proportional gain for the joint. And what we've noticed is that we actually don't have to tune those. We can use the biological value because they are rendered accurately by the quasi-direct drive actuator. Whereas with more traditional designs, like our earlier design of our Gen 1 leg, if you plug in a biological value, well, then you have to do a bunch of tuning to account for the fact that the actuator has its own dynamics. And so you're not actually rendering the desired impedance at the output. And so you have to do a bunch of tuning to get something that is close to what you actually want in the end. And this is a problem that afflicts most robotic leg designs in the field. And we've been able to get around that. During the swing period, as I mentioned, we're going to be using something called a phase variable, which was a concept that was pioneered by Professor Jesse Grizzle at Michigan. And so the idea is that we take a mechanical measurement from the robot that happens to evolve monotonically with respect to time. So we see here that the phase variable is strictly increasing with respect to time during a steady gait cycle, which means that you can actually reparameterize the joint angles, which maybe you define first as a function of time. You can then reparameterize that as a function of phase because you have a one-to-one relationship between time and your phase variable. And the reason this is really nifty is that if you're walking and suddenly you stop mid-gait cycle, and maybe you hold where you stop for a period of time, so it's like a phase shifting perturbation where you've held your trajectory. Well, then the joint angles of the robot will also freeze during that holding period. And as soon as you let go of the robot and let it continue to move forward, well then the trajectory continues from where it left off, as if nothing had happened. And so when you look at that over the phase variable, if it's a purely phase shifting perturbation, well then you actually don't notice any disturbance in this plot whatsoever, because of the fact that the phase variable accounted for that phase shift that we see in the time domain. So now to implement this on a robotic prosthetic leg, we have to measure something from regarding the human body that is predictive of the human body's progression through the gait cycle, so that we can control the distal limb segments in a predictive manner. It has to be measurable from a prosthetic leg. And so we settled on the thigh angle of the amputated side. So essentially, we're measuring the angle of the residual limb of the above knee amputee. And the reason that the thigh angle is really useful for this purpose is that it has a nice sinusoidal trajectory where we're during swing phase essentially is that increasing the ascending portion of the cycle, where we can then take that monotonic trajectory and map it to our desired joint angles using this continuous sense of phase in the gait cycle. And again, we're using an IMU that is mounted to the top of the knee hinge of our robotic leg, which then gives us the residual limb angle. So this video actually demonstrates our one of our first human participants learning how to use this phase variable controller and actually having a lot of fun with it. So you can see that he ends up swinging around with it because he realized that he's able to control the knee and ankle motions with his hips to stay synchronized with the swinging motion. And that really kind of nicely demonstrates the phase variable concept. Also, we're able to walking without using walking aids like handrails. We're able to walk very comfortably. They're under control of their own walking speed through the phase variable. During steady treadmill walking, we really see the benefits of this controller during stance phase. We see this really smooth touchdown, smooth transition to flat foot, and then actually push off that propels the gait cycle, propels the prosthetic leg into swing. And then the hauling of it takes over and control the foot placement. Swing period. So again, nice rhythmic, smooth, stable gait pattern. So we ran a study with 3 above knee amputee participants, the case series, where we looked at the effect of the robotic leg compared to the conventional passive leg that the user was originally prescribed by their clinician. And so we noticed pretty consistently that ankle push-off power increases, which is to be expected. There are a couple cases where a participant didn't stay in stance phase long enough to fully embrace the powered push-off, but generally speaking, we saw higher push-off power. That contributed to a increase in stride length, which is a positive outcome. And for 2 of the 3 participants, we noticed a decrease in the pull-off power on the residual hip, meaning this is occurring during late stance to early swing when they're pulling the leg into swing phase. And of course, our robotic leg is heavier than their passive take-home leg, but because it's providing a really powerful push-off, it actually helps launch the prosthesis into swing. And for those subjects that really embrace the push-off, they stayed in stance long enough to get it, they benefited from that and had reduced hip power as a result. And then we look at hip work, which is in our case is the sum of the positive work and the negative work, the absolute values of each, just to show the total work in each regime. We see a decrease in hip work for the powered leg compared to the passive leg. So our next steps include modeling and control for continuously varying activities, including stair climbing, uneven terrains, outdoors, maybe even running. And we have a current NIH project on that. And in closing, I just want to mention that we're also using this quasi-direct drive paradigm for exoskeletons as well. And this is particularly useful for populations that have some residual control over their legs, but maybe they're weakened or they are susceptible to fatigue, and therefore they need some torque assistance. But they still want to be in control of their kinematics. They want to be able to determine where their leg moves. And that's where back drivability is key. And commercially available exoskeletons, unfortunately, are way too stiff and rigid to allow that in the way that someone with weakness would be able to leverage. So that is ongoing work for in our exoskeleton side of things. So I just want to thank you for your time, thank my funding sources, and of course the fantastic team that made this work possible. And I look forward to discussing this work with you throughout the workshop. Thank you.